For a long time, physicists pictured the inside of a solid metal exactly like this, a microscopic box filled with a chaotic, random swarm of free electrons bouncing around just like gas molecules. According to this classical ideal gas model, if you apply heat to a material, every single electron inside that box should absorb energy. The math strictly predicts a constant heat capacity for all electrons, regardless of the temperature. But in real-world experiments, especially near absolute zero, the actual measured heat capacity is drastically lower than the classical prediction. This diagram shows the quantum reality that breaks the classical model. Quantum mechanics packs electrons into specific energy states up to a rigid boundary called the Fermi level. Only the few electrons sitting within thermal reach of this outer edge are capable of absorbing heat. This illustration reveals the physical solution. Electrons do not exist in an empty, free-floating void. They navigate through a perfectly organized crystal lattice of positively charged iron cores. This grid creates a periodic modulation, a repeating energetic wave that constantly pulls on the electrons. To predict how a real material behaves, the free electron gas model is completely inadequate. We have to mathematically incorporate the exact physical structure of the crystal lattice itself. This side-by-side comparison shows how we map that physical environment. On the left, actual physical atoms are arranged in real space. On the right, physicists translate that grid into reciprocal space, defining an exact elastic scattering circle, dictating where wave collisions happen. Because electrons possess wave-like properties, they diffract through this atomic grid. The Bragg condition defines the exact momentum boundaries wherein an electron wave will stop passing through the empty space and instead perfectly reflect off the atomic structure. This graph illustrates the exact moment of perfect reflection at the Brillouin zone limit. When an electron's wave vector reaches these dotted boundaries, the left-traveling and right-traveling waves reflect and crash into each other. They superimpose to form fixed standing waves. This table details the two physical outcomes. The even wave probability peaks align directly on the positive ions, causing maximum attraction and a low energy state. But the odd wave peaks shift into empty space. With minimum attraction, it is trapped in a high energy state. At this precise momentum boundary, an electron must exist as either the high energy odd wave or the low energy even wave. It cannot possess any energy value in between. That physical gap in electrostatic energy is the exact origin of the band gap. This diagram shows the mathematical framework required to calculate these states for an entire macroscopic crystal. Physicists use a boundary condition trick, assuming the linear crystal loops back on itself in a giant ring. Because the electron's wave must seamlessly connect with itself at the ends of this loop, its momentum can no longer be a continuous sliding scale. It is mathematically restricted to precise, discrete, quantized values. This graphic demonstrates Bloch's theorem, the rule governing how these quantized electrons move. As the multiplication at the bottom shows, the electron propagates as a standard plane wave, multiplied by a localized, repeating wobble induced by the atomic lattice. This reveals a crucial physics distinction, shown by the crossed-out math here. Because the periodic amplitude term creates its own mathematical gradient, the electron's wave is not an eigenfunction of the true momentum operator. The lattice dictates electron behavior so heavily that we track its movement using a specialized quantum number called crystal momentum. It accounts for both the electron's free movement and the physical momentum transferred directly to the atomic grid. This slide shows the rigorous math required to calculate these energy states. Analyzing a periodic potential in real space is nearly impossible, so physicists use a Fourier expansion. We translate both the physical lattice potential and the electron's wave function into reciprocal space. But when we plug those expanded series into the Schrödinger equation, a structural problem appears. The infinite sum representing the atomic lattice and the infinite sum representing the wave have different summation indices. This highlighted box explains the algebraic trick to solve it. By taking the middle potential term and shifting its summation index, substituting k with k minus g, we force all the exponential terms in the equation to perfectly match. This perfectly aligned math gives us the central equation. Looking at the labeled components, it groups together the kinetic energy of a free electron, the true energy eigenvalue we want to solve for, and a lattice scattering term that couples the states together. The central equation mathematically proves that an electron inside a crystal never exists in isolation. The periodic physical structure forces it to continuously mix with a specific set of other momentum states. This stacked set of formulas shows the immediate consequence of that mixing. Because state K is strictly coupled to K minus G, which is coupled to K minus 2G, solving for a single energy level means solving an infinite system of linear equations. This determinant matrix repackages the infinite system. Kinetic energy terms run down the center diagonal, with periodic potential coupling off diagonal. Setting this to 0 yields energy eigenvalues. Near the Brillouin zone edge, it truncates to a 2x2 grid, allowing us to calculate the band gap. This chart recaps the math's evolution. The free electron gas failed to explain heat capacity. Incorporating the periodic potential fixed this, proving standing waves exist. Finally, we solved these interactions using the central equation and its determinant matrix. This continuous refinement of the math is exactly how solid-state physics bridges the gap from chaotic classical particles to quantum waves. The resulting energy gaps give us the definitive structural reason why one material conducts electricity, while another acts as a perfect insulator.